Hi, welcome to the Olympiad geometry. Let's continue our study on geometry treasure. Today we're going to talk about the Steiner theorem on concurrent perpendicular lines. So for the first theorem, let A prime, B prime, C prime be the points on edge BC, CA, AB in triangle ABC. So we can draw the figure as here. We have A, B, C, and we have 3 points there on each edge, respectively. Then the lines that passing through each point and perpendicular to the side it lies on are concurrent if and only if this equation, right? Basically, it's saying that if we can find a point P in the triangle ABC, actually it's fine if it's outside. And we find the perpendicular lines that are passing through P to each edge. Then we can call A prime, B prime, C prime here, right? So we want to prove that if PB prime is perpendicular to AC, PA prime is perpendicular to BC, PC prime is perpendicular to AB, then BA prime square minus A prime C square plus CB prime square minus B prime A square plus AC prime square minus C prime B square equals to 0. Right, that's for the first case. And if this equation is valid, then if this equation is valid, then the lines, let's see, A prime P1, which is perpendicular to BC, right? Perpendicular to BC. B prime P2 is perpendicular to AC, and C prime P3 is perpendicular to AB. So we know that A prime P1, B prime P2, C prime P3 are concurrent. Right, we want to prove these two cases. So for the first case, it's much easier, just because if we know that P is a point and we find the perpendicular lines that passing through P, which means we find the foot of each perpendicular lines, then we can directly write that BA prime square minus A prime C square, right? BA prime square minus A prime C square, which equals to BA prime square plus A prime P square minus A prime P square minus A prime C square, which means we can combine these two, right? It equals to PB square minus PC square, right? BA prime square plus A prime P square, that is PB square, and A prime P square plus A prime C square, that is PC square. So we get this one. And similarly, CB prime square minus B prime A square equals to CP square minus AP square, right? And we have AC prime square minus C prime B square, which is C prime square minus C prime B C prime B squared, that equals to AP squared minus PB squared. And if we add these three equations, we got that PB squared minus PC squared plus PC squared minus PA squared plus PA squared minus PB squared, which equals to 0. Right, we just proved that. Now we think about the case that we want to prove that these three, so if this is true, we want to prove that these three perpendicular lines are concurrent. We can consider that A prime P1 and B prime P2 are concurrent. No, are intersected on the point P, right? So we can think as just because we have A prime, B prime, and we make the perpendicular line, these two perpendicular lines intersect on the point P, right? Then we know that if we find a perpendicular line from P to AB, we call it, for example, C. We call it C prime prime. Then we know that BA prime square minus A prime C square plus CB prime square minus B prime A square plus AC prime square minus C prime B square equals to 0. This is from the problem set. And we also know that based on, we just proved that because PA prime and PB prime and also PC prime prime are all perpendicular to each side, that means the BA prime square minus A prime C square plus CB prime square minus B prime A square plus AC prime prime square minus C prime prime B square equals to 0, right? And if you look at these two, that basically tells us that AC prime square minus C prime B square equals to AC prime prime square minus C prime prime B square, which means AC prime minus C prime B equals to AC prime prime minus C prime prime B, right? Which means C prime is the same point to C prime prime, right? That is saying if we find the perpendicular line that passing through C prime and perpendicular to AB, then it concurrent on the point P. Okay, that's Steiner theorem. And we have the second theorem. Okay. In two triangles, let me just draw it. In two triangles, triangle ABC and triangle A prime, B prime, C prime, right? So we have triangle ABC here. I will draw the triangle here, right? So for now, we just draw two lines here, and let's call it A, B, C. You will see why I want to draw this way. So in these two triangles, if the lines passing through A, B, C and perpendicular to line B prime, C prime, C prime, A prime, A prime, B prime, respectively, are concurrent, right? That means the lines that are passing through A, B, C and perpendicular to these edges are concurrent, right? Then the lines passing through A prime, B prime, C prime and perpendicular to line B, C, C, A, A, B respectively are concurrent. Okay, so now we want to find the perpendicular lines roughly say this is perpendicular line, okay? And we want to find this one to here. So it's about like this, right? And we know that these lines are concurrent, so we can first find the perpendicular line here, and we just need to find another line perpendicular to this line, right? So let me just draw it. Right. We can set here as B prime, then we know right, roughly say this is perpendicular. So then we know this is A prime, this is C prime. Right, so we draw that three perpendicular lines passing through A, B, C, and perpendicular to B prime, C prime, passing through point B is perpendicular to A prime, C prime. Passing through C is perpendicular to B prime, A prime. And these three lines are concurrent on this point. Let's call it D, right? Now we know these three lines are concurrent. And we want to prove that the lines passing through A prime and perpendicular to BC, which is like this, right? We want to prove that this line and the line passing through B prime and perpendicular to AC I feel it's more like here, right? Yeah, this is more like perpendicular. Forget about this line. Okay. So this line here. Now we find this point. And we want to prove that C prime, if we do a perpendicular line passing through C prime and it's perpendicular to AB, we want to prove that these three lines are concurrent here, right? Let's just think about how can we prove these three lines are concurrent. Remember that we just proved the first Steiner theorem. Means that if we can prove these things, we can prove that the three perpendicular lines are concurrent, right? So in here, let's just give the name of the intersection points. So first we have we have the lines that are passing through A perpendicular to B prime, C prime. We give this name as A1. And we have the points that, we have the line passing through A prime and the perpendicular to BC meets BC on another point here. Let's call it A2. Okay? So this point is A2. This point is A1. Similarly, for the points that passing through B and perpendicular to A prime, C prime, we call this B1. We call this point C1. And think about that we find the perpendicular line that passing through B prime and perpendicular to AC meets AC on the point B2, right? For this one, it's neglected that it's concurrent. We don't know, we want to prove that, right? So C passing through C prime and perpendicular to AB, we call this intersection point as C2. Now our target is to prove that AC2 squared minus C2B squared plus BA2 squared minus A2C squared plus cb2 squared minus b2a squared equals to 0. We want to prove this one, right? If this is true, that means the perpendicular line passing through A2, the lines that are passing through A2 and perpendicular to BC, the line passing through B2 perpendicular to AC, the line passing through C2 and perpendicular to AB. These three lines are concurrent, which is the lines that the perpendicular lines are passing through C prime, A prime, B prime, right? So we want to prove that this is true, and this is target. And what we already know, we know that because this line, the AA1, BB1, and CC1 are concurrent on a point, which means we have, like, let's start from this one here, B prime A1 square minus A1 C prime, right? A1 C prime square plus C prime B1 square minus B1 A prime square plus A prime C1 square minus C1 B prime square equals to 0. That's what we know. Okay, now let's look at this equation. We have the B prime A1 square minus A1 C prime square. It can be rewritten as B prime A1 square minus A1 C prime square equals to B prime A1 square plus A1A square minus A1A square minus A1C prime square, right? It equals to B prime A1 square plus A1A square minus A1A square plus A1C prime square, right? And we know that B prime A1 square plus A1A square, which is AB prime square minus here A1A square plus A1C prime square, which is AC prime square, right? It equals to this one. And what is AB? Right? What is AB? AB square can be rewritten as BB2 square minus AB2 square, right? So it equals to BB2 square minus AB2 square. Oh, wait, sorry. It's AB prime, right? AB prime. So AB prime, because this is 90 degrees, this is perpendicular, AB prime equals to AB2 square plus B prime B2 square. So it's B prime B2 square plus AB2 square, right? That's AB prime square. And for the AC prime square, right, we just find the AB prime square. For the AC prime square, it equals to AC2 square plus C prime C2 square, right? Which means we basically use the first problem set, which we has a B prime and A1, right? All of the relations are the A, B, C, and but we have the A1, B1, C1, but we can translate it into the expression with B2, C2. But we don't have the A1, B1, C1. We have A2, B2, C2, right? And that meets the target. So let's continue. For the BA2 square minus, for this one, for C prime B1 square minus B1A prime square, right? For this one, C prime B1 square minus B1 A prime square, right? It equals to BC prime square minus BA prime square, right? This one and this one. Square root of this one minus square root of this one, that equals to square root of this one minus square root of this one, right? And it equals to BC prime can be rewritten as BC2 square plus C prime C2 square, right? So equals to BC2 square plus C prime C2 square minus this one, BA prime square, which equals to BA2 square plus A2A prime square. And for this one, we have A prime C1 square minus C1 B prime square. A prime C1 C1 square minus C1 B prime square, which equals to A prime C or C A prime square minus C B prime square, right? And it equals to, so we have CA prime square. This one here, it equals to CA2 square plus A prime A2 square, CA2 square plus A prime A2 square minus CB prime square, which equals to CB2 square plus B prime B2 square. Right? We know the summation of these three equals to 0. So we have the summation of these three should be 0. Now we extend this one. Right? So these three, the summation of these three should be 0. Let's extend it. So we have B prime B2 square plus AB2 square minus AC2 square plus C prime C2 square plus here should be minus, right? Plus BC2 square plus C prime C2 square minus BA2 square minus A2A prime square. And plus CA2 square plus A prime A2 square minus CB2 square minus B prime B2 square, right? So B prime B2 square, these two cancels, and we have C prime C2 square minus plus, so these two cancels, and we have A2A prime square, which is A prime A2 square, right? That's this one, right? A2A prime A2 square. So these two cancels, right? And we have let's see what else we have here. Yeah, so it equals to 0, which means AC2 squared for this one. So let's use another way, which means minus AC2 squared, right? And plus C2B squared. C2B squared, right? So these two. And then we have minus BA2 squared. And plus A2C squared, right? And then minus CB2 squared. And plus B2A squared equals to 0. You can see this one just has a negative sign difference of this one, right? So this is 0, that means this is 0. Then we just prove that the perpendicular line passing through C2, B2, A2, and the perpendicular to BC, AB, AC, BC respectively, are concurrent, which means the C prime C2, B prime B2, and A prime A2 are concurrent. Okay, that's the second theorem. And now let's look at the conclusion here. Conclusion is saying that finds the perpendicular lines to line L that passing through vertices of triangle ABC, right? So basically, we would have, I can directly write that here. So we can think we have a triangle ABC here. And we have a line L. So we find the perpendicular lines to L that passing through vertices of triangle ABC, right? So we find this line here, this one here, and this one here. Let fit to be A1, B1, C1. So we have B1, A1, C1. And we know that A2, B2, C2 are on BC, AC, AB respectively, and A1, A2 is perpendicular to BC. So this one is A2, and this one is B2. Right, it's not necessarily concurrent here, but this one is C2. Right, now we want to prove that A1, A2, B1, B2, C1, C2 are concurrent. This figure is not that clear, so let me redraw it. So this is line L, we have A, B, C here. We find the perpendicular line from A, B, C to the line L first. Right, so we have B1 here, A1 here, C1 here, and we know that this is A2, and I want to find the perpendicular line. Yeah, roughly see this is a perpendicular line. So this is C, and this point here is C2, right? And now we want to prove that, sorry, this is B2 and this is C2. We want to prove that C1, C2, B1, B2, and A1, A2, these three lines are concurrent on here. right? That's what we want to prove. And it's basically the same idea that we want to prove AC2 squared minus C2B squared plus BA2 squared minus A2C squared plus CB2 squared minus B2A squared, right? We want to prove that this equation equals to 0. We want to prove this equation. And what is AC2 squared minus BC2 squared? It's basically AC1. So it is AC1 squared minus BC1 squared, right? And the AC1 squared can be rewritten as AA1 squared plus A1C1 squared, which equals to AA1 squared minus that is AC1, right? A1 squared plus A1C1 squared minus BC1 squared, which is BC2 squared plus C1C2 squared. So here is a minus sign. We have BC2 squared minus C1C2 squared, right? And for the second one, BA2 squared minus, something wrong here. Yeah. So BA2 squared minus A2C squared, that is BA1 squared minus A1C squared, right? So it equals to BA1 squared minus A1C squared equals to BA1 squared, which is BB1 squared plus B1A1 squared minus A1C squared, A1C squared, which is CA1 squared. CA2 squared minus A1A2 squared. Right, and for the third one, we have we want to prove that CB2 squared minus B2A squared, and CB2 squared minus B2A squared equals to B1C squared minus B1A squared, which equals to B1C squared, that is B1C1 squared plus CC1 squared, right? Minus B1A squared, which is B1BA squared. Sorry, B1A1 squared minus AA1 squared. Okay, now if we sum these together, we see that AA1, and here is plus AA1 minus AA1. And we have A1C1 squared here. Wait, we don't have A1C1 squared somewhere? It doesn't look correct. Let me see. Hold on. Let's just check on the rest part and we will find out the bug, right? So we have BC2 squared here. We have C1, C2 minus this one here. So let's keep this one. We have minus sign, plus sign. Wait, C1, C2. 1 second, something wrong here. Why it's AA1? It should be A1, A2, right? So we have B1A squared, B1A squared. Oh yeah, it's B1A squared. It is AA1 squared. It looks correct. What about here? Hold on, let's review this again. We want to prove that AC squared minus AC2 squared minus C2B squared plus BA2 squared minus A2C squared plus CB2 squared minus B2A squared. This is correct, right? That's our target. And consider about AC2 squared minus C2B squared. AC2 squared minus C2B squared. So it equals to AC1 squared minus CB1, BC1 squared. And it is correct, right? So it equals to AC1 squared minus BC1 squared. And AC1 squared can be written to be AA1 squared, right? Plus A1C1 squared. So that is obviously true. And then minus, for here we have the BC1 squared, which is BC2 squared and C1C2 squared. So this is definitely true. And for the second part, we have BA2 squared minus A2C squared, which is BA1 squared minus A1C squared, which is true. And BA1 squared can be rewritten as BB1 squared plus BB1 squared plus B1A1 squared. That's true. And minus this square, which is A1C1. Oh, here, right? So A1C squared, that equals to A1C1 squared. A1C1 squared plus CC1 squared. So yeah, I made a mistake here. So this one should be CC1 squared. Is that correct? A1 A1C squared. So CC1 squared. Wait, where is C2? Something wrong here, actually. Let's go back. AC1 squared, it equals to AC1 squared minus BC1 squared. That's true. And AC1 can be rewritten as AA1 squared plus A1C1 squared. That's true. And BC1 squared should be BB1 squared, right? BB1 squared plus B1C1 squared. Yeah, okay, and here we got C minus C1A1 squared minus CC1 squared. That's correct. Now we have it. Great. And then this part should be CB2 squared minus B2A squared. CB2 squared minus B2A squared, which is B1C squared minus B1A squared. Right, B1C squared minus B1A squared. That's true. And B1C squared is equals to B1C1 squared plus CC1 squared. That's true. And B1A squared equals to B1B2 squared. Right, B1A squared equals to B1B2 squared. And AB2 square. So we have this part should be minus B1 B2 square minus, wait, hold on a second. Let's see, B1A square, this one equals 2. Oh, here, B1A, we want to use B1A1 square plus AA1 square. So B1 equals 2 minus B1A1 square minus AA1 square. Okay, now let's see. We have AA1 here, we have AA1 here, we have A1C1 here, and we have A1C1 here, right? We have BB1 here minus BB1, and we have plus BB1 minus B1C1 square plus B1C1 square here. So we have plus CC1 square here minus CC1 here, and plus B1A1 here minus B1A1 square here. Yep. And we just prove all of these equals to 0. Right. So this part is not difficult. It's just because once you connect this line can be represented by this square of AB1 can be written as B1 B2 or plus B1 B2 square plus B2A square, or B1 A1 square plus A1 A square. Just keep in mind we want to remove all the two parts, right? Like C2 B2 A2 parts. So we want to use A1 B1 C1 only. So that's the thing confuse us. Okay. That's a series of that's a Steiner series, and I think this I've seen this kind of problem before, that you want to prove the 3 lines are concurrent, and actually you need to find a way to transfer the problem into this. Okay. I hope you like this video. If you think this is helpful, please click the like button, comment, share, and subscribe to the channel. Thank you. See you in next one.